Earlier this chapter, we learned that there were two different types of compounds, and each type was named a little bit differently. Molecular compounds were named using the prefix system, but the prefix system was only used for naming molecular compounds. Anything that was ionic, we used the stock system for. The hardest part about naming compounds so far has been identifying, is the compound a molecular compound or is it an ionic compound, which is something that we need to know to decide which system to use. For that reason, we can simplify things by using the stock system for all compounds, both ionic and molecular compounds. But there is one problem with doing this. The stock system typically has Roman numerals telling us the charge of the ions. In a molecular compound, there are no ions, so there would be no charges, but yet we still use Roman numerals. The Roman numerals have a little different meaning for molecular compounds in the stock system. The Roman numerals actually used to identify the oxidation number or oxidation state of the first element. Now, oxidation states are numbers that don't really have a true scientific meaning or definition. Basically, what they do is they show the distribution of electrons in a bond. In chapter 6, you learned that one element typically attracts electrons more strongly than the other one in a bond. The more electronegative one tends to gain greater control of the electrons and take on partial negative charges. So the oxidation state or oxidation number is just showing us which element tends to have stronger control of the electrons. They're very useful in naming compounds, and we also use them in studying chemical reactions. Now, there are a couple of simple rules to follow. There's actually 7 rules. The first rule is that atoms of an element that are pure, that are by themselves, always have an oxidation number of 0. That's kind of like saying that when atoms are in a compound with other atoms of the same element, they have no charge because they evenly share the electrons. The electrons don't gravitate towards one side or the other, so there's no partial charge. So any element that's by itself has an oxidation number of 0, and any element that's only with other atoms of the same element have oxidation numbers of 0. For example, the oxygens in an oxygen molecule attract electrons equally, so their oxidation number is 0. And the same thing is true in a molecule of sulfur, which has 8 atoms of sulfur. Each one has the equal attraction for the electrons. We also assign oxidation numbers in the same way that we do charges, which is in any compound, you start with the second element, you assign it a charge, and you work backwards to figure out the first. Well, for molecules, the more electronegative element in a compound is assigned the number equal to the negative charge it would have if it were an ion. So we start with the second element, we give it an oxidation number equal to what its charge would be, and then we work backwards to figure out the oxidation numbers of the other elements. There are 3 elements that have special rules. The first of the 3 elements is fluorine. As you know, fluorine is the most electronegative element there is, which means in every single compound, fluorine will always gain control of the shared electrons. For that reason, fluorine always has an oxidation number of -1. Another element with special rules is oxygen. Oxygen is also a very electronegative element. In almost every compound, its oxidation number is -2. There are a couple of exceptions to this. For example, peroxides. Peroxides will always have 2 of a group 1 element bonded to 2 atoms of oxygen. For example, H2O2. The oxidation number of oxygen in this compound is -1. Superoxides, which have a group 1 element and 2 atoms of oxygen, always have an oxidation number of -1/2 for the oxygen. And lastly, when oxygen's bonded with fluorine, because fluorine is always -1, when oxygen's with fluorine, as in OF2, oxygen has an oxidation number of +2 instead of -2 because it has to offset the electrons that are being pulled more towards the fluorine. The last element that has a special role is hydrogen. Typically, hydrogen has an oxidation number of +1, which is not surprising because typically hydrogen forms ions by giving up 1 electron and having a 1+ charge. The only exception to this is when it's with metals. With metals, hydrogen has an oxidation number of -1 because it tends to be more electronegative than the elements paired up with. In other words, the electrons will be pulled more towards hydrogen, not towards the metal. The other rules deal with adding together all of the oxidation numbers in a compound. Rule number 6 states the algebraic sum of the oxidation numbers of all atoms in a neutral compound is equal to 0. That's just like charges. When you add up all of the charges of any crystal or any compound, the charges will always balance out to 0. So same thing in a molecule, all your oxidation numbers add up to 0. The algebraic sum of the oxidation numbers in all atoms of a polyatomic ion is equal to the charge of that ion. So if you add up the oxidation numbers of all of the elements in sulfate, they'll add up to -2 because the charge of sulfate is a 2-. And remember, all 7 of those rules are used to explain how we assign oxidation numbers to mainly to atoms that are covalently bonded, but the rules actually apply the same way to ionic compounds and ions. The only difference is the oxidation number is not just showing electron distribution, it's showing true charge, where the electrons actually belong, which atoms they belong to. All right, let's take the compound uranium hexafluoride and use that to look at oxidation numbers. We begin with the element that is known. In UF6, we have a rule that deals with fluorine, and we always look at our 3 special rules, fluorine, oxygen, and hydrogen first. Our rule is fluorine is always -1, so we assign fluorine an oxidation number of -1. There are 6 fluorines, so that means the oxidation state of all the fluorines would be -6, because -1 times the 6 atoms would be -6. We can then assign the oxidation number to uranium. We know that the uraniums will have to total +6 because it has to balance out the -6 in fluorine. Because there's only 1 atom of uranium, that 1 atom of uranium has a total oxidation number of +6. Now, when we look at this, we can assign them just like we do charges. We started with fluorine and we gave it a -1. We then looked at the -1 over fluorine and noticed it was the same as the subscript on uranium, so we reverse cross and we take that 6 from the fluorine and put it above uranium. But since fluorine was a negative over uranium, it has to be a positive. Couple of differences in how oxidation numbers are written as opposed to charges, and in this compound they're kind of obvious. You can see in this compound the -1 over fluorine as an oxidation number. It's written as a negative sign and then the number, whereas charges were always written the opposite way, the number, then the sign. So as a charge, it would be written as 1-. As an oxidation number, it's written as -1. The other difference is it's not in the upper right-hand corner of the element. We actually typically write it directly above the element instead. All right, this compound is oxygen hexafluoride. It is uranium hexafluoride. We name it in the stock system as uranium 6, Roman numeral 6, fluoride. Now, stock system works the same way for molecular compounds as ionic. We just use the Roman numeral to show the oxidation number of the first element instead of the charge. So it's name of the first element, uranium, in parentheses a Roman numeral 6, Vi, indicating the oxidation number of uranium, and then the name of the second element with the ending changed to "ide", so fluoride. The rules also explain to us how to assign oxidation numbers to a compound that has ions in it, or polyatomic ions. So in the next example, we have what are the oxidation states of each atom in sulfuric acid. Sulfuric acid's formula is H2SO4. Begin with sulfate. Sulfate is SO4. Its charge is 2-, so all of the oxidation numbers in sulfate will add up to a -2. Oxygen is the first element in sulfate that has a rule that we know. The rule is that oxygen's oxidation number is almost always -2. So I wrote a -2 over oxygen. And I noticed then, since there's 4 atoms of oxygen, they would total an oxidation state of -8. Now, the oxygen and the sulfur added together have to give us a -2. If oxygen is -8, we ask ourselves, what number do we add to -8 to get a -2? And the answer is +6. Since there's 1 atom of sulfur, that atom of sulfur has an oxidation state of +6. Now, if there were more than 1 atom of sulfur, we could take that +6 and divide it by however many atoms there were. But in this case, +6, and we're done. Now, for hydrogen, we do have a rule that says hydrogen is almost always +1, which it is in this compound. But we can also figure out the oxidation state of hydrogen from sulfate. Since sulfate is -2, the hydrogen has to balance it out. So the hydrogens will total +2. However, since there's 2 atoms of hydrogen, that means each one is +1. So in this compound, hydrogen has an oxidation state of +1. The sulfate has an oxidation state of -2, but it's made up of sulfur with an oxidation state of +6 and oxygen with an oxidation state of -2. Let's look at the examples on this slide. For each one of them, to determine the oxidation numbers, we first begin by writing out the formula of the compound. The first one is nitric acid. We know all acids begin with a hydrogen ion, so our formula for nitric acid is HNO3. Start with the polyatomic ion and give it an oxidation number equal to what its charge would be. Polyatomic ion is nitrate, and its charge would be 1-, so all the oxidation numbers in nitrate will add up to a -1. Now we go with our special rules: fluorine, oxygen, and hydrogen. There's an oxygen in this compound, and it's almost always -2, unless it's a peroxide, superoxide. That doesn't apply to this compound. So oxygen is -2. We have 3 of it. So that totals a -6 for the oxygens in nitrate. What would the nitrogen be so that when added to that -6, we get a -1, which is the charge of nitrate? And the answer is +5. So the nitrogen has an oxidation number of +5. For hydrogen, there is the rule that the oxidation number of hydrogen is almost always +1. And we can prove that in this compound because if nitrate is -1, the hydrogen has to be +1 to balance it out. In example 2, potassium hydride, we have the formula KH. There's a rule for hydrogen that says hydrogen is almost always +1 unless it's with a metal, in which case it's -1. That fits this compound. Hydrogen is paired up with a metal, so hydrogen would be a -1. Potassium would have an oxidation number +1. In our third example, carbon tetrachloride, we don't have any of the 3 special elements, fluorine, oxygen, or hydrogen. So we start with the second element, which is the more electronegative, and we pretend it's an ion. What is the charge of chlorine as an ion? -1. So the oxidative state of chloride is -1, and there's 4 of it, so that totals a -4 for all of the chlorines. Carbon has to be a +4 to balance that out so that all the oxidation numbers can add up to 0. So carbon 4+, or +4 for the oxidation number, chloride -1. This one we could even name using the stock system, and we would get the Roman numeral from the oxidation number of the first element. So it could be called carbon, in parentheses, Roman numeral 4, which is IV, and then Cl, for chloride for the Cl. In our last example, tetraphosphorus dicoxide, the formula is P4O10. Oxygen has a rule that it's almost always -2, so the oxidation number of oxygen is -2. Because there's 10 of it, that means the total oxidation state for all the oxygens would be -20. That also means that the phosphorus must be a +20 to balance out the oxygens. But you have 4 atoms of phosphorus. So that +20 divided by the 4 atoms would be a +5. So phosphorus has an oxidation number of +5. If we were to name this in the stock system, it would be phosphorus, in parentheses, a Roman numeral 5, which is a V, followed by the word oxide to represent the oxygens. In the last two examples, I used the stock system for naming the compounds. We can use the stock system for a molecular compound or an ionic compound. The rule is, though, we have to know the oxidation state of the first element, just like we had to know the charge of the first element for ionic compounds. The oxidation number of the first element is always indicated by the Roman numeral in the name of the compound. Let's take a look at this example, the stock system name for phosphorus trichloride. Phosphorus trichloride is PCl3. There's one phosphorus, we know that because there's no prefix. The second element, chloride, has the prefix tri, so there's three of it. We begin oxidation numbers with our special elements. None of those are in this compound. So we start with the second element, which is the more electronegative, and we work backwards. Chlorine, if it were an ion, would have a charge of -1. So that's its oxidation number. But there's three of it, so the oxidation state of all the chlorines would add up to a -3. That means that the phosphorus, to balance it out, would have to be a +3. And there's only one phosphorus, so a +3 on phosphorus completely and totally balances out the -3 on chlorine. And naming it in the stock system, we use that oxidation number, Roman numeral 3, in the name, and it becomes phosphorus 3-chloride. So notice, we're not doing this with prefixes anymore. We're naming them just based on our oxidation numbers, which work just like charges. Take a look at the examples on the next page. First one is phosphorus pentachloride, or PCl5. Again, three special elements aren't here, so we start with chlorine, give it an oxidation number equal to what it would have as a charge, which is -1. There's 5 of it, so the chlorines would add up to -5. My phosphorus, on the other hand, would have to be a +5 to balance it out. And the stock system name would become phosphorus 5-chloride. Example 2, dinitrogen monoxide. Dinitrogen means two nitrogens. Mono oxide is one oxygen, so it's N2O. Start with oxygen. The rule is oxygen is almost always -2 unless it's a peroxide or superoxide. This is not a superoxide because the first element's nitrogen, not one of our metals from group 1. So N2O, oxygen has an oxidation number of -2. There's only one of it, so the nitrogen has to be a +2 to balance that out. Unfortunately, there's two nitrogens, so that +2 is divided between the two nitrogens, and each one is +1. That means the oxidation number for this one is +1 for the nitrogen, or nitrogen 1 oxide. It's important to note here, although I haven't been doing it, you can notice how we're still reverse crossing the charge. Because the subscript, or rather the oxidation number on oxygen matched the subscript on nitrogen, that also means the subscript and the oxidation number from oxygen will match the oxidation number of nitrogen. So we can reverse cross the charge. In the next example, nitrogen monoxide, there's one nitrogen and one oxygen, so the formula is NO. Oxygen still is a -2 for the oxidation number, so nitrogen has to be +2 to balance it out, and the name would be nitrogen 2 oxide. In lead dioxide, we have the formula PbO2. Since oxygen has an oxidation number of -2 again, and there's 2 of it, that means the oxidation state of the 2 oxygens would be -4. Lead would have to be +4 to balance that out. So the stock system name would be lead 4, Roman numeral, O2, or lead 4 oxide. Next one, dimolybdenum trioxide, 2 molybdenum, so it's MO2, O3 for the 3 oxygens. Again, we have oxygen, which has an oxidation number of -2 in most compounds. So -2, there's 3 of it, so the oxygens total -6. Molybdenum has to be +6, so each atom of molybdenum would be +3, and it would be molybdenum, Roman numeral 3, oxide. Again, note how we can reverse cross the charges because those numbers are the same. For the last example, As2S3, As2 in the prefix system would be diarsenic, and S3 would be trisulfide. So the prefix system name would be diarsenic trisulfide. For a stock system, sulfur is our starting point for oxidation numbers because it's more electronegative. It's the second element. So if sulfur were an ion, it would have a charge of -2. That's its oxidation number. -2, reverse cross the charges. You notice the charge matches, the oxidation number matches the subscript on arsenic. So we know the oxidation number of arsenic will match the subscript on sulfur, and it becomes +3, or arsenic +3 sulfide. Now, thinking that out, remember we have 2 sulfurs, so that means the total oxidation state of sulfur is -6. The arsenics would be +6 to balance it out, so each one would be +3.